Alright, welcome back everybody. Today we continue with the mass spring systems, as you can see here on the slide, and dig deeper into the actual simulation algorithms. Alright, let me start. So to quickly recap, last week I introduced Hooke's law, very fundamental, very important. We'll be using it a lot in the next weeks. Most importantly, you can see that part here, the length of the force proportional to the change of the length of the spring, and then here we have the direction part. And I also introduced this this bit higher level summary of the different terms as the equations of motion. So Newton's second law, m times acceleration equal to forces on the right hand side, and the important bit here was that we have different derivatives of the position, namely the second one for the acceleration on the left, and then a first one, the velocity, no derivative, the position directly for the internal forces, and then an external term that does not depend on the position at all typically. Yeah, so this is our basis. That will be what we're using for the simulations. Now I do want to use this point to quickly illustrate a few of the aspects of springs, and for that, usually in class, I can bring a few springs and really give them around so you can take a look. Well, you all know what springs are for. One interesting thing is that normally if you buy a spring in a store, they come in different types. So this is a spring that that actually compresses and bends, and in contrast there's one that's specifically manufactured to only extend. So it's a pretty tough one, but you can see it actually can bend it. This one has a very high stiffness, very stable, and this one is specifically manufactured to extend. Now, if you think about Hooke's law, we have this one parameter, the k, that determines the amount of force we get at the endpoints of a spring from the spring. And if you think about this one, here the force I get from pulling is actually very different, like to the one from compression, right? This one is actually extremely difficult to compress even a tiny bit, whereas this one here, this one, right, I can actually compress relatively easily, and I can also pull it apart. So that points a bit to the potential limits of such a physical model, especially one like Hooke's law that is relatively simple, a linear model, clearly has limits. One way to think about this is if we basically plot on a graph. I quickly want to sketch this here. If we imagine having a graph here where along y we have the magnitude of the force, and along x we have the change of the length of the spring. So basically you could call it the delta L. We typically looked at the actual length. Now I'm looking at the change from the endpoint. What we are doing with Hooke's law is we are basically taking a line where the tangent, the steepness of that line, is given by this stiffness k. If we have very high k, then the line would be very steep, and correspondingly smaller k's give us smaller forces. And if you now think about what a real spring does is, well, actually we're looking at the change of the length. We really need to look at both ways. So this line would go to zero meaning there is no change, and then it extends to both sides. And a real spring, if we choose a good model, actually does behave linearly around the 0 point. So here in the middle we would have something that is very much in line with this with the increase determined by k. But typically, as we grow on and on, in reality typically the forces increase and grow steeper, And in practice also, if we compress more, at some point it would grow, like with this spring here. It becomes, the force is actually huge at some point. Although I should, if I plot the force here, sorry, I usually plot this in terms of the signed force. If, as indicated here, we have the magnitude of the force, then we actually would have such a curve. And here still around 0, we should actually see this okay, and then the forces would increase. And one thing to note also, as we grow towards the right side, we stretch more and more. At some point the spring will break, and then it might actually drop down to 0, continue at 0, just to illustrate a bit this behavior. So typically around the rest point, this linear model of Hooke's law is actually a good approximation. Here around 0, this holds quite well, not just for springs, also for other physical settings. But as we go away from this rest state, potentially there are more nonlinear effects, and then we would deviate from this linear change. Today I want to talk a bit about implementation aspects to basically get you started with implementing this. I'll also get back to that later for the first exercise. And then, in a way, we'll take a step back and look at some of the fundamental principles behind simulations with this straightforward approach. So from last time, we had these fundamental relationships. Velocity is a change of pressure, acceleration is a change of the velocity. And in, for example, the game design lecture, you might have come across it in different settings. We have this Euler step as one of the key building blocks of such a simulation. And with that, we can actually integrate or advance the velocity and position forward in time. And the way to do this is relatively straightforward, right? So we have here this relationship basically tells us the velocity is the change of position over time. So in practice, what we can do is the position at a time t plus some delta t, or h as we'll typically call it, is actually the position at time t plus h times the velocity at time t. Right, that gives me the new position at time t, and then for the velocity I can do a similar Euler step now with the acceleration at time t. And in this way, then here I now have two new quantities for a new time step. That's my new state, and then I can repeat that. So that's a very simple process that we can more or less out of the box compute. And well, in a way, the interesting bit now is we have these springs. So in order to compute this Euler step, we need to evaluate the springs, i.e. we need to evaluate Hooke's law a couple of times, accumulate all the forces, and then divide by the mass of a point to get the acceleration. But that's actually relatively easy to implement in practice. So here's one suggestion what that might look like in an implementation. We probably need some structure to encapsulate a spring. One way to do this would be to basically have two pointers. Here I am assuming that basically these index into a list of all the points. So here at position I have a certain mass point I that is indexed by this integer, and same for point 2 for the endpoint. And then in addition, I need some specification of the physical characteristics of the spring, i.e. its stiffness, the k parameter that we had before, and its initial length, that was the capital L. What about the current length? It's actually also on the slide here. We can store that, but that's actually not necessary if you think about it, because the current length is given by the points, by the endpoints. So if we have these links to the points, we can always compute the current lengths from their positions. But in practice, it actually might not be a bad idea to just store it. Typically, you need it more than once. So it can be useful to have this the current length of the spring for a given state of your system in such a class or struct. Yeah, the mass points for the mass spring system are also quite straightforward. We need to store these key properties. The position, definitely, we need to know where the points are. We need to track the velocity over time, also a very important component. And then another quantity that here is recommended is the force. Effectively, the force does not carry over to the next step, right? This is not something that actually builds over time or so. Position and velocity change continually over time based on the previous values. The forces determine the acceleration of the current step and are actually not depending on the previous acceleration. So theoretically, we could leave this out. However, in practice, we always, for a time step, somehow need to compute an acceleration. We do that by computing force divided by mass. Hence, we need to somewhere store the accumulated forces, and it is actually a good idea to do that in the point so that you could display them or check for debugging. The mass here is also stored per point. I mentioned last time it's typically the same, but nonetheless, right, for flexibility, both mass and damping are stored as per point variable parameters in this example. And then the simulation loop would progress in a pretty straightforward manner. So first we have, in a way, a loop over all the points here for cleanup. So here first we clear the forces, reset the force vector entry. Might as well, while we're at it, add gravity again. Typically all the points start a time step by experiencing the acceleration from gravity. Now we are actually have clean state. Now we can incorporate the internal forces from the spring connections, and here that is done in the following, or so the suggestion here is to do it in the following way. We loop over all the springs, and for each one of the springs we one time compute the elastic forces, this F vector from Hooke's law, and then this one we actually in a way only need once. We know from Hooke's law it acts with both signs to the endpoints, so once we have it we can add it to both of the springs. It's listed separately here. In practice this goes together nicely, and then once this loop is computed we have evaluated all the internal forces, added to all the endpoints. The force accumulators have the correct value. Now we can go ahead and compute the new position and acceleration. So the important thing is, I'll come back to that a few times later on. We could now, with these elastic forces here, go ahead and compute a new velocity from the acceleration, and then with this velocity compute a new position. However, this is not a good idea. Don't do that. That is actually a different method in practice. So what's important for a normal Euler method is to not use these change velocities again, but we are now at time t. With the velocities of time t, we now want to update the positions, hence this step. And afterwards we can change the velocities. We actually, such a step, typically don't need them anymore. Then we can update the velocity values. But it's important that for a regular, correct Euler step, we use the velocity of the previous time step in order to update the positions. Yeah, just to mention it, what's actually recommended in this Millington book is a slightly different way. So he introduces mass per mass point force generators. He has a separate generator class that is basically registered at a mass point, and then each mass point have queries and evaluates all the force generators that link to it. It's also a nice interface for these generators. However, in this case you actually need a spring twice, because each generator only adds to one point it's connected to. The spring has two endpoints, hence you actually need two of these generator instances for one spring, which I think is a bit unintuitive. Typically we think of the spring as one object. However, this is also it's an alternative that's recommended in the book there. Another point that in practice is quite important for somewhat interesting simulations is that we have some form of collision. If you don't have any collisions, you just get freely bouncing mass points in free space. A good way to test, but in practice, for something a bit more interesting, you'd want to introduce some collisions. That typically is, or the easiest starting point to do that is the following. You can compute positions and then basically clamp all negative positions to 0. That effectively gives you a collision plane at the position 0. And on first sight, that might be a bad idea. You essentially simply squash everything into the ground at 0, right? At the 0 level with this. If you have an object and it goes too far into the ground, it's simply compressed into the plane. For a mass spring system, it's actually not so bad because we have the springs. We have some internal structure for the object, and these springs will then push back and inflate the object and let it collide from the ground. So for a starting point, I can actually recommend adding at least a collision plane in this way. That will already be a good test. We'll have a whole chapter later on collisions where we'll go into more detail about how to detect and handle collisions. Yeah, another note on heavy objects, heavy meaning in this case typically infinitely heavy. So if we have objects that essentially don't participate in the simulation, that are static, like a wall of my room or so, theoretically it has a mass. I could incorporate it, but it's a huge mass. It would need a very large force to move a wall like this. So in the limit, as an approximation, you can assume objects like the environment have an infinite mass, and effectively that means, we actually, if you think about the F equal m times a equation, the acceleration divides by the mass, hence infinite mass means the resulting acceleration will be 0 no matter what the force is. And if you want to do this even slightly faster, what you could do is you can basically flag objects that have an infinite mass rather than trying to divide by something huge. So basically you can flag these objects and then say, yeah, these objects really don't experience any acceleration. Yeah, so even what you can also do is basically fix individual points in this way. They say that one point is extremely heavy, it does not move at all. If there are springs connected to it, then we basically have a fixed point that will pull back the points around it. For example, with some with a Boolean flag as part of your mass point class. Yeah, so much for the basic rundown of a first mass spring simulation algorithm. Based on these recommendations, you should be able to implement the first version. The first exercise will be along those lines, actually implementing a mass spring system. However, the core goal of that one is to actually evaluate a few of the different techniques that I'll introduce in a moment. So now we have a basic simple version. Now we can basically think about how to do it better in a way. Yeah, so as mentioned before, now we can basically take a step back. Let's look at what we had so far. I hope you can see this here. We had our equations of motion. So acceleration being dependent on internal forces, depending on the position, other terms, and the damping. And yeah, in practice, in reality, we actually might have quite complicated functions that depend on the position here, right? The whole equations of motion basically revolve around this x, around the positions of our points. But these different functions that are introduced here, especially the internal forces, might actually internally do pretty complicated things. So we cannot just easily evaluate this. But the structure that I've mentioned before a bit, it actually becomes clearer if we rewrite that, if we shorten the notation a bit, if we leave out all the dependence on time of x, right? Kind of know that x is a function of time, and that we have multiple points, and in this version as it's written down here, right? So this is maybe a bit more clearer that this is acceleration. Here we have the external forces, some function of x, internal forces, for example, and the first derivative. And now it's very clear that we have the structure. We have a second derivative, external, 0, and first. Now, this you could write in notation you might be used to from school. If we denote a derivative by one of these dashes, essentially now, if we also bring the mass over, we have an equation that says the second derivative, or acceleration, is actually a function that depends on the time, surely. All of the x depend on time, right? On the x and on the first derivative of x, the velocity. And this f now internally bundles up all this behavior from before. And now you can actually see the structure here. We have a differential equation, we have derivatives of our position, but they're all with respect to time, just with different orders. And that is what's typically called an ordinary differential equation, or in short ODE. There are, as the name implies, ordinary, there are different ones. I'll briefly come back to that later, but for now we can actually look at those. They're by themselves very interesting. Yeah, so far we've talked about mass spring systems. In the following, we'll be talking about these ODEs and methods dealing with ODEs, because in a way, traditionally, this is a different topic. I want to change the notation a bit. So we had the x for position. In the following, we'll have x as a free variable. What used to be time is now the x. Hence, for ODEs, typically we have a function y of x that computes later on the state of an object, but for now we can basically treat this as just some function that depends on x, and y is the function we're interested in. So just keep in mind for now, x for the following slides is not the position anymore, but is what we so far treated as time. It's basically the variable that we want to integrate over and that we want to evolve. Yes, so x replaces time. Yeah, for these ODEs, key is that we have one free variable and derivatives with respect to this free variable. So in this new notation now, you can see it here, we have an ODE of nth order, and it depends on ODE, meaning ordinary differential equation, and meaning we have the nth derivative of y being a function of typically all the previous ones. Right? You can imagine here in this f we have all kinds of different components. Some of these factors or the influence could be 0, but in the general case it can depend on all of these derivatives, and the highest one actually determines the order of the ODE, and if you want the complexity, hence that's the most important one. All the other ones we bunch up in this f on the right hand side. Now one way, or one good way to think about it, is we now have this function f that gives us a higher derivative. So if you look at this, right, here we have a higher derivative. If you imagine we actually now cut this off and we say we only look at the first part, then we have an ODE of first order, meaning this is 1. The first derivative is a function of x and y. That's actually a relatively simple case that you can look at first. And for this case, right here's f of xy, we can actually look at it in this plane. So now keep in mind we're now actually looking at essentially different values of x and y. This is not just a simple 1D function, but we have all these points in our plane, and for each of the points we have there, this function f gives us a derivative of y. So what we will do with that typically in practice is that we have a trajectory, we have something we want to check over time later on, right? So we basically follow this direction, and we are at a certain point along a line. And now this function f of x and y at this point gives us the derivative of y, and tells us basically how y changes along the y-axis naturally. And the important thing to note is we do not just now have one of these curves, but this whole space could be filled with curves that we could theoretically track, right? We could be interested in all kinds of different curves along this plane, and essentially that's illustrated a bit here on the right side. Essentially we have a whole 2D vector field where for each of the points in the plane here we have a change along y in this case for the highest derivative, in this case the first one. Yeah, so this is set up in a way. What we'll typically be dealing with is we have a current state of our system, some point on this yellow curve, and now we want to follow as accurately as possible, compute the trajectory along that curve. Yeah, so for first order or ODEs, as mentioned before, this is the shape we're having, and there is actually a whole theory on ordinary differential equations. They come up in quite a few situations, and here is one example that's written out here. So we have the derivative of y with respect to x plus y divided by x is equal to -4. Here now, in order to find a nice solution, we're actually assuming that x is larger than 0. And I don't want to go into details here. This is in a way well known. You could look this up, but for all kinds of basic ODEs, you can actually look up solutions. And in this case, there's actually a very nice one. Hence, that's why I chose this example. So in this case, you can show that y is actually equal to some constant c divided by x minus 2x. And c is actually a constant that now is necessary as an integration constant that we need to determine by initial conditions. So, for example, if we're given an initial state y of 1 being equal to 1, then we can insert that and solve for c and determine that here, as you see in this example, you have 1 and then -2, you get a value of 3. In many other cases, you actually get some logarithms, but yeah, there is a whole field of literature on solving these basic ODEs. One note here, or a few more points that are worth noting. One point is, we're dealing, if you think back to the mass spring system, we're actually dealing with second order equations, right? Imagine we had, think back, we had the acceleration on the left-hand side for Newton's second law. Hence, we have something on this of this form. So I think now we're out of luck. Things will get much more complicated, but it's actually no problem at all. You can show that any higher order any higher order ODE requires a suitable number of initial conditions now for all the derivatives on the right hand side, in this case y and y dash, and then you can find solutions by breaking down the higher order ODE into a system of lower order ones. So for the second order one, we can break it down into two first order ODEs. In this case here it's shown as a slight renaming. So we have one first order equation here for a y1 dash. So the derivative of a y1 depending on y2, and then we compute the derivative of the y2 by a function of the y1 itself and y2. It's a bit like what I already showed before. You can basically first integrate something like the acceleration and then integrate the velocity over time to get the position. And you can basically also do this for any higher order ODE. All right. One comment about these this solving process. These problems where we are starting at a certain state for x. Right, remember, we typically walk along the x-axis, called initial value problems, because we're given the initial state and then we want to find its evolution. There are also boundary value problems which play an important role in practice, where if you have more free variables, you can basically give constraints on the side. They're a bit trickier to solve. For these ODEs now we'll actually stick to initial value problems. Also looking ahead a bit, there are a large class of physical problems actually are partial differential equations. The key change there is that we have not only derivatives with respect to one variable like the x before, but we might have functions that depend on multiple variables, and our model equations might have derivatives with respect to several parameters. And then it's not ordinary anymore, but then we have partial differential equations typically, because we have derivatives with respect to these different parameters. So typically it's written in this way. Here now we have a function y that depends on a z and a t. T might be time and z some kind of other parameter. And here now we have one derivative with respect to time, and here, for example, a second one with respect to this z parameter. And this now would not be ordinary anymore because we actually have time and z here. Yeah, and in practice, boundary value problems for these PDEs, those are very important in practice. All right, now a few more comments on ODEs while we're at it, so to say. There is a whole class of analytic solutions that I want to mention here because they're so fundamental. They come up a lot, and that is especially or kind of intuitive if we think about having a single spring that's fixed at a certain point, say to wall here as illustrated in this picture. And now we're interested in this orange mass point at the bottom. And also traditionally you would now again change the coordinate system a bit and say what we're interested in is not the actual spring length, but we're interested in right from the rest length how much is this point displaced. And yeah, if we formulate it in this way, the force is just minus k, stiffness constant times the displacement, that's x. That's pretty simple. Typically we need some initial conditions, so in this case, for example, an initial displacement, and the ODE that we have in this case is in a way also a very fundamental and simple one. The acceleration is now so minus k times x divided by the mass of the point, And from this ODE, we actually get solutions that are called harmonic oscillations. And this is something that comes up a lot, again, also in circuits or in quantum states or all kinds of systems. So as you can imagine, we basically have the spring and we have a point, we drag it somewhere and then it oscillates. Right? If you plot this over time, you basically get a sine curve that changes. And now you can, the solution actually tells you a few nice things, namely that the amplitude depends on this initial condition, but the frequency depends only on the stiffness and the mass of the point. So that's actually one pretty fundamental and a nice thing. That is a property of these harmonic oscillators. So no matter how much we drag initially, the frequency will be the same. It's just that the amplitude, how far it moves, will change. So, and then we have a cosine basically. This is really a pretty fundamental thing, and we can also make it a bit more interesting by including a damping effect. Then we get with this gamma parameter e to the minus gamma t term that reduces the oscillations over time, and with that we get oscillation motions that are actually already quite realistic or happen in a similar manner in many situations. It's basically a damped sine curve, that cosine curve, that goes down and decreases over time. It's still very simple though, so if you think about doing anything a bit more interesting and complex with this, that typically doesn't work. You can extend it with some tricks to 3D, but going beyond single springs is really challenging here. And yeah, if you think back about the example I had before, like simulating clothing or tissue of characters, that will not really work with this solution. So these analytic solutions are definitely very nice. If we have something like this cosine function, that's great. That will not blow up or give us any weird answer, but just the right one at a certain time. But it's extremely simplified. This is actually not useful in practice and not possible for mass spring networks. And that is why we will now actually put these analytic solutions to rest. And this is something that we cannot use in practice. Rather, what we will be looking at from the next chapter on are approximations. We're trying to find a solution that will not be as exact often, but it will be something that we can compute for complex scenarios. And that is the main next goal here. All right, and that is a good endpoint for this chapter.